So we're going to be looking at a CSTR, a continuously stirred reactor, in which a first order reaction takes place. So we have a reactor with a constant volume V. We have an inflow F. Remember, that's cubic meters per second or liters per minute, liters per second, or any other matching unit. And the inflow has a concentration, which I will call Cn, of some compound. Let's name it A. So this compound A is poured into the reactor. We can imagine there's some enzyme or something else in the reactor which makes the compound A react so that it is converted into another compound B. And so there's also an outflow here, F, and it's the same as the inflow rate here. So there's going to be a constant volume inside the tank. Now the reaction is assumed to be a first order reaction, and that means that the reaction rate, which we will typically call R, is equal to some reaction constant K times the concentration of A. And since it's the first order, not second or third or whatever, it's a first order reaction because it's the first power of C that we have here. And because A is the reactant, it's the one that's converted, we will put a minus here because the reaction rate tells us how much substance is created per liter per second. And since A actually disappears, we can say that a negative amount is created. So the minus here is because A is a reactant. R has units of moles per cubic meter per second, or moles per liters per second. So it's an amount of substance. It's an amount of substance per volume per time. Okay. What we want to achieve is an expression which tells us what the concentration of the compound A is inside the tank as a function of time. And to achieve that, we will state a molar balance, or a mole balance, which is the same as a mass balance, except that we're keeping track of the amount of substance instead of the mass. And the molar balance looks like this. The incoming number of moles per time unit, how many moles per second enter the reactor, plus how many moles will react per second. And in this case, we know that A is going to be consumed, but it could be that it was created. But in general, we'll just say that it reacts. And then how much of A accumulates inside the tank per second. And finally, how much leaves the tank through the orifice here per second. That's the molar balance. And let's try to be more specific. The incoming amount of substance per time unit can be written as the flow rate times the concentration. Notice that all of these terms, of course, they have the same unit, and that unit would be moles per second or minute, whatever time unit we use. This term here, let's check the units. Cubic meter per second times moles per cubic meter. That gives us moles per second, so that's a correct unit. The amount of moles that react per second, we will write as an integral of the reaction rate possibly it's a function of the location in the tank. So we have to integrate this rate, reaction rate, across the tank volume. Let's look at the units. This one has units moles per cubic meter per second. This has units cubic meters. So we will end up with moles per second, which is fine. Then we have the change in the amount of substance of A inside the tank. We can write that as a differential. How much does it change per time unit? And you can see that that has moles per second as well as a unit. And finally, the outflow of compound A can be written as F times, well, what's the concentration of the outflow here? Well, we will assume that it has the same concentration as inside the tank, because we will assume that the tank is well stirred, hence the name stirred. That means that there's the same concentration everywhere in the tank. That's something we assume, at least. So the outflow is going to have that concentration. So I can put that into the equation here. Because the tank or the reactor here is stirred, that means that everything is mixed up. So the reaction rate is going to be the same everywhere because the concentration is the same everywhere. This means that R is not dependent on the location in the tank. So we can take it outside the integral. It's just a constant. So we're integrating over this reactor volume here. We might put that in here in the integral. So that means this integral, which is actually the number 1 in here, we don't write that. It's just going to give us the reactor volume. I'm not changing anything over here. And here we can insert, we know for a fact that the amount of substance in general can be written as the concentration times the volume. I needed an equality sign here, sorry. And then we have the flow times the concentration. Now, since we have the same flow in as out, the volume is going to remain the same inside the tank here. So that means that V is a constant, which means we can take it outside the differential. And all that's left now is to substitute this expression here for R into the equation. So that gives us minus K C A V F C N. And now we have a differential equation for CA. We can see that we have the derivative here, and we have the function itself here and here, like that. Let's put it into standard form. I'm going to do that by collecting the terms of CA. So I'm going to take this over here, B dCA dt, and then I'm going to move this to the right hand side, which is the same side as this term here. So we're going to get F plus KV CA is equal to FCN. And in order to bring it to standard form, I'm just going to divide by V everywhere in all terms. So we're going to end up with a differential equation looking like this. Like that. Now we can see that this differential equation is first order, because it's only been derived once at most, we can see that it's linear, and we can see that it's inhomogeneous. Because this term over here on the right hand side is not 0, so it's inhomogeneous. And we're going to solve this equation using the general solution formula. So let's just remind ourselves what that solution formula looks like. So this is what it says. It tells us if we have a differential equation which looks like this, and that's indeed what we have. We have a first order derivative and then the function times some expression here and another expression on the right hand side. Well, in that case, the solution will be this. It involves the exponential of capital P of t, and the capital P of t is the integral of P of t, that is this function here. So let's look at the actual differential equation we have. Here it is, and if you compare it to the general differential equation here, we can see that this is our P of t. It's not actually a function of t, but that doesn't matter. And this over here is our R of t. And the function that we were looking for, x, is now CA. So we're just the first thing we have to do is to find capital P of t. So capital P of t is then the integral of P of t, which is f plus kv divided by v t. That's a quite easy integral because this is just a constant. So what we're going to get is f kv by v times t. And then we're ready to plug it into the solution. We get e minus capital P of t, which is this function here, times the integral of e to the power of f plus kv by vt times fcn by v. So that's the r function here that we have here, dt, plus the arbitrary constant, like that. Okay, this is not as bad as it looks. This part here is a constant. We can take it outside the integral. And furthermore, when we integrate this function here, I mean, it's just e to the power of some constant t. The integral of that is going to be 1 over alpha times e to the power of alpha t. So if we use that and take this constant outside, what we're going to get is e to the power of f plus k v v t times, take the constant outside, and 1 over alpha would in our case be 1 divided by f plus kv divided by v, and then e to the power of f plus kv divided by vt plus c. And if you look at this expression for a short while, it can actually be simplified because v here cancels with the v here. And in fact, this exponential cancels with this because it's the same exponent except for the minus, so they cancel out. So what we end up with is fcn divided by f plus kv plus c1, and then this exponential here will be multiplied by this constant here. So we get e minus f. And I really should put brackets around here. Sorry about that. Same here. Like that. And then I might want to, this is the general solution. So this is any solution, all the solutions to this problem here. If I'm looking for a particular solution, I have to specify initial conditions, ICS, and let's just choose a very simple one. At time 0, there is no concentration. The concentration is 0. There's no amount of substance inside the tank to begin with. And if we use this condition, what we get is, I should put an A here. What we get is FCNF plus KV plus C1 times e to the power of this constant, and then I'm setting t equal to 0. Has to be equal to 0. Right. So this part here, because I set t equal to 0, this is going to be 1. So all it says here is C1, and then I can move this bit here to the the right hand side. So I'm going to get this expression for C1, and then I can substitute that back into my general solution. So I'm going to substitute this expression into the general solution to achieve Ca of t is equal to, and if you note, this expression here is the same as this expression except for a minus sign. So this can actually be simplified quite a bit. I can factor out this constant here. You can work it out yourself if it's a little too fast. 1 minus e to the power of minus f plus kv by vt. So that's the particular solution here. If you look at this function, this exponential here, at t0 it starts being 1. As t grows, it becomes smaller and smaller and smaller and until it approaches 0. So this is going to be a graph which starts at 0, at time 0, and then it's gradually going to increase, approaching this constant here, but it's never really ever gonna make it, but it's getting closer and closer.